to introduce today's speaker, Professor Thomas Schön from Uppsala University. Professor Schön received his PhD degree in automatic control in 2006, and before that, his master in electrical engineering and a bachelor in business administration and economics, all from Linköping University. Since 2013, he's a full professor at Uppsala University, first at the chair of automatic control, and since 2020, he's the Bayer Professor in Artificial Intelligence at Uppsala University. And he has held several visiting positions and won several awards, both for his research and his teaching. And in fact, it was his teaching that made me interested in estimation and system ID in the first place. And his research has been a great source of inspiration for me over the last 10 years. And I'd say that his research lies in the intersection between control and learning, often relying on probabilistic models to cope with uncertainty that is present in any measurement data. And some concepts of his specialties include particle filters, Markov chain Monte Carlo, Gaussian processes, and deep reinforcement learning. And today we'll talk about deep probabilistic regression, and I give the floor to Thomas.
Thank you so much, Carl. Thanks for the invitation. So what I'll talk about today is regression problems and how we can solve them using deep learning. So this is joint work with one of my students here, Fredrik Gustafsson, and a colleague at ETH, Martin Daneljan. And there are some references here covering most of what I'm saying today. So the main message I have is that the combined use of probabilistic models and deep learning is probably more interesting than we think. And I'll try to drive that through by formulating and solving various regression problems. Of course, there's been, some of you might have heard about something called the variational autoencoder, which is one particular construction that is on this theme. But again, we'll focus on regression problems for now. So the key takeaways, or the key takeaway, at least for me, from modern machine learning is that these flexible models often gives us the best predictive performance. So if that is true, the next question is how can we build and work with these flexible models, I guess. And of course, we have deep learning, which is a large but fixed number of parameters. And then you have non-parametric models like Gaussian processes. So these are two different ways in which we can do this. And one should be quite careful when working with these flexible models, since they can indeed be deceptive, and we've seen quite a few examples of that throughout this pandemic, I guess. But again, done right, they are extremely useful, and they can indeed be combined with other background knowledge we might have. But for now, let's look at a problem, a typical deep learning kind of problem. So I'm borrowing this from some of the applied work that I do on in medicine with ECG, so electrocardiographical data. So this is recordings of the electrical activity in the heart, which is a very useful diagnostic tool, low cost, fast, in terms of figuring out what happens in the heart. And there we have shown that by a fairly straightforward application of deep learning, we are reaching human level performance on specific tasks. So we have looked into 6 of the most common ECG abnormalities and been able to show that we are on par with humans in making these predictions from ECG data. And the key difference to the classical approach here is that the model is not derived based on our ability to explain what we think we might see in the ECG, but instead, as you probably know, in deep learning, we take a generic model that automatically learns suitable features based on a large data set. So that was our edge here together with our friends in Brazil, we have a massive data sets with almost 2.5 million ECGs, and with both the inputs, so the curves, and the outputs, what the medical doctor said was going on in this heart. So again, this is yet another example of more or less standard use cases for deep learning. But what about regression problems? So that's something I came to think about more than 2 years ago now, I guess 2.5 almost. How do you make use of deep learning to solve regression problems? Turns out that has not been properly settled, I would say. But let us make this very concrete by looking at something called a nonlinear autoregressive model with exogenous inputs, or a NARX model. So I'll explain what it is in case you haven't seen it before. So here we assume that our output depends on past outputs and past inputs. So envision a classical dynamical systems scenario. And the goal, if you want to solve this probabilistically, is to find the distribution, conditional distribution of the outputs based on all the previous outputs and the previous inputs to the system. And the challenge is, how should we choose this predictive distribution? And the straightforward option that's used in many solutions is to come up with a functional form for this. But if we do that, that leads at least to 2 questions. So first one is, how should we actually parameterize this distribution? And once you have decided upon that, then the question is, how should you learn it, or how should you estimate these parameters from the data? So if we look at what the classical answer to these 2 questions is to assume that the output equation looks like this. So the output is some nonlinear function of x, and again, x was here defined as the previous outputs and previous inputs to the system. And then you have some noise on top of that measurement. And then the solution, I mean, this predictive distribution is then dictated by the assumptions that we make on E, on the noise here. And how should we then figure this out, find these parameters from the data? And traditionally, we make use of maximum likelihood to do this. And for example, assuming that you have Gaussian noise, that leads to the following problem when we make use of maximum likelihood. Which is all good and fine, and for many applications that is enough. But one could question here, why not use a more flexible model? I mean, even if so, this is what the way I used to think of using deep learning for prediction. Just use a deep neural network to represent this function f, so it predicts the outputs. But by doing that, we miss a lot already from the start, so to speak, because we have then implicitly assumed that the answer, this predictive distribution, is a Gaussian distribution, which it typically will not be. So we have said that it will have one mode, and we have said that unlikely measurements cannot happen, and so on. And why would we want to do that when we have all the flexibility here, and then we sort of ruin it at the end? So what if we could come up with a better way of doing it, where we don't ruin it in the end, so to speak? I will try to make this clearer soon. But I just picked this as one particular example from the area of system identification in this case. So a slightly more general question then is, how should we best formulate and solve regression problems using deep learning? So this is what I want to talk to you about today. And we're using examples from computer vision to illustrate solving regression problems from computer vision to illustrate the methods that we have developed. And this is an example of target tracking that I will come back to, which we can formulate as a regression problem, where the problem is to regress the coordinates and the size of this box, which is following this dog as it's playing with this other dog in the snow here. Okay, let's step back a second and properly formulate the problem. So it's supervised regression, so we have access to both inputs and outputs or targets, X and Y. And we have a data set, training data set available to us, where the data comes from some unknown distribution, which we of course can never have access to. And a deep neural network is just a big function that's parameterized by theta and maps the input to an output. And again, with a probabilistic take on regression, the task is to learn to figure out this conditional output distribution, so the distribution of the output conditioned on the input. And first, I'll give you an intuitive preview, informal preview of the construction. So it's a general method which has a clear probabilistic interpretation. And we make use of something called an energy-based model, which some of you might have heard of before. If not, I'll define it soon. The nice thing with this energy-based model is that it allows us to use highly flexible target densities that we can learn from data. So I do not have to come up with an assumption of what this distribution looks like, which is one of the key benefits here. Here's a little toy example to illustrate what I mean. Let's say that your distribution, the ground truth distribution, looks like this. So the input and the output. So here it's clearly bimodal, and over here it's like a skewed Gaussian distribution. So if you restrict yourself to a Gaussian distribution for the target distribution, and then learn that as good as you can, you get something that looks like this, which is not completely off, but of course you have no chance of figuring out which mode you're in. Instead, you're trying to cover everything. Whereas with our method, you can get a better grasp at what the actual distribution looks like. All right, so that was a bit of an intuitive preview to put your mind into the right region, so to speak. So what I'll do now is be a little bit more specific about how people have solved regression problems using deep neural networks before. I classify them in 4 different categories, and then I'll talk about these so-called energy-based models, explain what it is, and then show you our construction and walk you through a few examples or a few experiments where we have put this to use. So again, when it comes to classification, deep learning is, I shouldn't say sorted out, but I mean, we have standard losses and standard representations for dealing with this. So we have a pretty good understanding of where to go. And again, when it comes to regression, it's quite different, I would argue. And in fact, the current standard practice involves the use or dictates the use of very simple unimodal distributions. Either it happens very implicitly, so you're perhaps not even aware of that it's going on, or very explicitly where it's postulated. So let's see what has been done before. So I'll start by something we call direct regression, which the NARCs example I gave you is one particular example of this, but slightly more abstractly. What we do is we train a deep neural network F to directly predict the target output Y from X. And we learn the parameters by coming up with some form of loss function that is makes us pay a price when the prediction and the corresponding measurement is different. And the way we pay that price is described by this loss function. And then we sum over all the data to get the cost function and solve that problem as good as we can. And quite common losses are the L2 loss or the L1 loss or some combination with a bit of regularization and what have you. And if we do that, then we are solving a maximum likelihood problem for a very specific model of the conditional target density. So you can sort of, so even if you just start from this optimization problem, it implicitly entails assumptions on the noise. So you can come up and see what kind of probabilistic model you're actually working with. Again, for example, the L2 loss corresponds to using a Gaussian assumption with a fixed variance. And then the networks come into play in the mean value here. So when people realized that, they thought about came up with something that we call probabilistic regression. And they say, well, why not try to use more flexible models, sort of what I've been trying to advocate here, but they restricted it to parametric models like Gaussian or Laplace distributions, and then played the following game that we use the networks to figure out these parameters. I call them phi here, and then we'll learn it typically by maximum likelihood again. So now we have a bit more freedom, I mean, in terms of the way the deep neural networks are used, but we still restrict upfront. We restrict the solution to a particular family. So, for example, a one-dimensional Gaussian model is then realized in this way, where the network outputs both the mean value and the variance. And it's trained using maximum likelihood. So this gives us a little bit more freedom and improves performance to some extent. And then a couple of years back, people in particular in computer vision came up with this very tailored model, I should say, called confidence-based regression. So these are more specialized, and the deep neural network is now trained not to predict the parameters for a particular probability distribution, but instead some kind of confidence value. So they predict some scalar function f here, which takes as input importantly both the input to the network is both the input and the output in the data set, so both x and y. And then we maximize this function to get the output. So this is very broadly described. But the key here is that we have both the input and the output present in the network. And then training the parameters, it's a bit of black magic, and you have to come up with all sorts of task-specific tuning knobs, which is what is a bit challenging with actually using this class of methods. But still, they could show that they get better performance. So there's definitely things to be learned from this class. And the fourth class is to sort of give up and say, let's just discretize the output space and into a finite set of classes and then use standard classification techniques. And I guess if that works, that's fine, but it has lots of quite serious inherent problems that you can never get away from. I mean, like proximity cannot be represented very well, and going into higher dimensions, it sort of explodes. So let's see what we did. So that was a very broad, or my personal broad painting of what is being done when it comes to using deep learning for solving regression problems. So let's see what we can do to improve this. So these so-called confidence-based regression models, as I say, they do give very impressive results, but it requires us to make some important and very tricky task-dependent design choices. I'm not diving into the details there now. And there is usually a lack of a clear probabilistic interpretation. Probabilistic regression, on the other hand, is quite straightforward and generally applicable, but it usually cannot compete in terms of regression accuracy. So we have tried to combine the benefits of these while removing some of the problems. And what we did is to make use of a model class that has been used for a long time in machine learning and physics under different names, but we refer to it as an energy-based model, which is a very simple idea. So it specifies a probability density, as I call it, P of X, parameterized by some parameters theta, by taking some scalar function f, and e to the power of f divided by the integral of the same object, then is by definition a probability density function, since it integrates to 1 and it's positive. So this is a neat way of coming up with a density function. And by then defining the scalar function f using a deep neural network, we can make use of the network to, based on the data, come up with an empirical description of the distribution itself. So we do not have to impose or come up with an assumption beforehand, which is a key to this approach. And again, this method has a long history in machine learning. I give you a few older references here, if you want to dive into the background. But again, the idea is fairly simple. That's what it is. Then, of course, there are challenging things if you start to think about how should you actually find the parameters here, theta. Well, then you would probably have to evaluate z along the way, which is then a pretty complicated integral. So there are definitely challenges to be thought about. So let's see how we can do that. But let's say it could be done. What is good about this? Well, the good thing is we can learn multimodal and asymmetric densities directly from the data. And the downside, or the cost, as I hinted at before, is that this normalization constant, or partition function as it's sometimes called, is intractable. And that is problematic because it means evaluating the predictive density is hard, and it comes into the into the likelihood function. So computing a maximum likelihood estimate is challenging, and if you want to generate samples from the predictive distribution, that is also challenging. Doesn't mean it can't be done. It's just that we need to think a bit about how to actually do this.
So Thomas, we have a question here from KJ. Please, KJ, go ahead.
Yes, in your this slide, T theta. So I think that there is a specific reason. So why we use like exponential function, because we assume that the underlying distribution is the Gaussian, then exponential looks okay, but in general, like a distribution, I just wonder, it is like an effective function of using exponential functions.
Mm. Yeah, let me go back to this slide perhaps so we see it even more clearly. That's a great question. Why use an exponential? So we can definitely use other functions here as well, and that's something that's interesting to think a little bit about. But before dismissing it all over, so the exponential family of distributions is actually quite very rich. It's definitely much richer than just the Gaussian distribution in terms of distributions for which we have names. Then we can fit a lot in that family. And here, when we let the exponent f be a nonlinear function, we get even more expressiveness in terms of the distribution. So it's much more general than the Gaussian distribution, as you saw from the first little toy example I showed you to try and illustrate that. But you're right, the choice of the exponential limits us a bit. So we still have made some kind of assumption here. So there's potential to think about others, but from what we have seen, we seem to get fairly far already with this one.
Just a quick point, KJ, to your question is, I guess you could also say the exponential forces the answers to be positive, right? So that's what you need in order for the distribution to be a probability distribution. Yeah, no, that is important, and whatever other function we use, we must ensure that it's positive. But that's good point. Good point. More questions?
I think we're all set to continue.
Yep, let's move on. All right, so let's look at the construction that we are using. So we let this deep network be a function that maps input-output pairs into a scalar value. And then we defined our energy-based model. And in this case, that's a technical thing, doesn't really matter too much. I mean, it's a conditional distribution because the density we are looking for is indeed a conditional distribution. And the way we do that is by integrating away the outputs and keeping the inputs. So let's say we are happy with that, and then want to think about how to actually train this object. And that comes down to finding a method to fit this density to the observed data, of course. And as we have said before, and as something that often gives us a good starting point is the maximum likelihood method. So then we set up this optimization problem, minimize the sum of the logarithms of this distribution. And if I do that for our class of functions now, the cost function will end up in this way. And the problematic part is, as I hinted at before, that we do not have access to this or closed form solutions to this integral. So that's the challenge. That doesn't mean we need to stop and do something else. It just means we need to think a little bit harder about what we should do to this integral. How can we approximate it? And when we start thinking about that, we should acknowledge that we're integrating over the outputs here. So for the examples that we have been looking at, which involves tracking objects in images, and we've also played around with estimating the age of a person based on a photo, and estimating the position and orientation of a head in an image, so to speak. So all of these are low dimensional problems in terms of the output. So they are very high dimensional in terms of the input, because the input is an image or a stream of images, which becomes high dimensional very fast. But the output is very low dimensional. So the position of an object in an image is just 2 dimensions. And if you then play the game with a rectangle around the objects, it's 4 dimensions. And if you do the same in 3 dimensions, then it's 6 dimensions. So again, we have, and the age problem is of course a scalar problem. So there's a lot of very interesting, from an applied point of view, interesting problems where this integral is low dimensional. So this is good news. And as Carl said, I've been working a fair bit with something called particle filtering, which is based on a statistical technique known as importance sampling, which works very well, especially for low dimensional integrals. So let's see if we can solve the problem using importance sampling. And if you haven't seen importance sampling, I'll explain it to you what it is. So again, this is just to remind you the problem that we have. That's what the model looks like. This is the integral that we need to approximate in order to solve the maximum likelihood problem. So what importance sampling does for you is to do the following. So this is the integral. Let's just look at the integral for now. Then we just insert q and we divide by q. So in that way, we have not changed the problem in any way at all. But we have opened up for a new way of computing the integral, actually. So if you think about an integral, you can think of that as the expected value of a function with respect to a particular distribution according to the definition of expected values. So this integral here is then the expected value of e to the power of f divided by q with respect to the distribution q. Right, so we treat this as a function, and this integral is then the mean value of that function with respect to this distribution q. And where does q come from? No one will give you that, but you are free to choose it on your own. So that's sometimes called the importance function or the proposal distribution. So what we did is we made use of, or what we did in the beginning is we made use of a Gaussian mixture centered around the measurements as our proposal, because that should give you something, intuitively speaking, give you something that's in the right ballpark for this integral. Turns out that works surprisingly well for a low number of samples. And then you have this approximate sum for the integral. And the problem with this solution is that when you go up in dimension, when y is 100 dimensional, for example, then this would not work so well. But again, quite a few relevant examples lives in low dimensions in y, so it's still relevant. And the most recent, I think I have a slide on that later on, but the most recent result that we submitted a couple of weeks back is where we actually learn the proposal distribution, because it's a bit annoying to have to come up with this on your own, but that we can actually take away.
So Thomas, we have another question here from KJ.
Yes. Yep.
Yes. So in my understanding, the objective of importance sampling is to narrow down the uncertainty kind of sampling, right? But in this case, you may use the Gaussian mixture. Then you may kind of more accurate mean and the variance, covariance to generate the sample right? But I'm not sure like what the kind of motivation of using the importance sampling. So the reason is that to narrow down kind of generation of the sampling for the next processing, or like what is the kind of general kind of objective of the use of the importance sampling in this?
Yep.
Works?
No, that is not the reason for why we use it. So the reason for why we use importance sampling is because it's a cheap way of approximating intractable integrals. That's the key reason. So you can use, depending on your problem, you can have different motivations for why you use importance sampling. That's definitely correct. And the reason I use it here is because, again, with a low computational budget, I can get a reasonable approximation, definitely good enough approximation of this integral. So this is the reason why we use importance sampling in this case.
Then the next question is that is a matter like what kind of like a distribution, for example, Q we chose for the generating of the samples. Is it important?
Good question. Yes, it is definitely important for the quality of your approximation. Theoretically, you can say if you just up the number of samples, everything is fine, which is true. So theoretically, it doesn't matter too much, as long as your distribution covers the support of the function, which most reasonable distributions do. So in that sense, the arrogant answer is that theoretically everything is fine. But the pragmatic answer is that it definitely matters, and the proposal distribution that you choose also determines the quality of your estimator. So that's why it's important to come up with something that's at least okay, if we put it like that. And from just playing around with concrete examples in the computer vision area and comparing to current state of the art, we could see that we could do at least as good and often better by just using this Gaussian mixture centered around the measurements here. And I guess the intuition why that might work is that we steer most of our computations towards the areas where the measurements are. So I think that's intuitively makes sense. But again, we can also look at the problem of actually trying to learn these distributions from the data. But that I haven't said much about yet.
Okay, thank you.
Yep, so Thomas, I think there was another question from Ankush, or did you have a question, yeah. Ankush?
Yeah, a quick question, Thomas. So looking at your first integral, do you think since you have this nice exponential form, could you use like Gauss-Hermite quadrature or maybe radial cubature type methods?
Yep, good question. Absolutely, I think that could be. There's good potential for doing something like that, or some kind of variational approximation.
Then you could avoid like trying to understand Q, right? Or guessing what Q is.
Yeah. So I think that can be done. It's just that haven't really looked into it, but sure. Absolutely.
Okay, thanks.
No more questions, I think.
Okay, let's move on. Good questions. So again, this was okay. Let's see what we did here. So we solved maximum likelihood that, or rather, we wanted to solve maximum likelihood. It gave us this integral. We had to approximate it, and we happened to do importance sampling. But as we just discussed, you can use any other decent function integral approximation method here. the important thing in terms of an application is that it has to be fairly fast. But as you just said, there are several methods capable of doing that. Let's see if then there is another way of solving the problem. So this is something that's not relying on maximum likelihood, but still delivering really good results. And to me, this was new, actually. So I've never seen this before. I think it was a reviewer who pointed this out to us, that we should look at this particular paper, which has proposes a method that they refer to as noise contrastive estimation, which is a general parameter estimation method which avoids the calculation of the normalization constant and its derivatives altogether. And I must say, if you find these kind of problems interesting, then I think you should look at this. To me, this is still interesting, and it's something I should look into a little bit more, actually. And the idea that they push forward is that we should learn to discriminate, to tell apart observed data examples and samples drawn from the noise distribution. And this is something that we, in this paper, we looked into this in quite some detail. And it turns out by using a modified version of this ID would require an entire talk to explain this in detail, of course, what this noise contrastive estimation is all about. But I'm just pointing to their paper for now and hinting at that this idea might be interesting. But what we could see is by generalizing it a little bit, we could actually get better results than what we could get from maximum likelihood. So there's definitely something interesting in their work here. But again, I'm not diving into details there. And then once you have trained your model, then of course you'd have a reason for why you do so. So you want to use your model at test time. And the way we have used these models is by simply predicting the target by maximizing the conditional output distribution, which can be criticized and I guess also intuitively understood, as in you pick the a posteriori estimate. So you have a probability distribution, and then someone asks you to give a specific answer. And then you pick the most probable one. Of course, you could pick something else, but this is pragmatic and straightforward in terms of giving one answer. Importantly, since we have the shape, or if we have an idea of the shape of the distribution, we could be able to say that we are in a situation where there are several solutions possible, and then refrain from picking one of them. So that we can do. And then we can worry about how hard is this to solve. And the good thing is that we have most of what we need to solve this already, since the gradients and everything has been can be very efficiently evaluated. So the computational cost is actually quite small to get these predictions out of your model. So let's have a look at a few examples. So let me explain the game a little bit more thoroughly than what I did before. So this is visual tracking. So we want to compute an estimate of the bounding box of the target object in every frame of the video. And the target object is defined in the first frame by someone drawing this initial box, let's say. So then the output, the Y, is the position of this corner, and it's the height and width of this box. So with these four numbers, you can then draw the box in every frame. But so this is the input to the algorithm, and then it needs to spit out these bounding boxes. See if I can show you a video of that. See, here is one example where maybe I should pause and explain what you see. So the red bounding box here is our algorithm, and the green one is a previous state-of-the-art solution for this problem. So the task is to track this person as he is riding his BMX bike in this half pipe thing. And then you can see that the other tracker gets lost and starts tracking the wrong person, and then eventually I think starts tracking the wall or something instead, so it's completely lost. And this is of course just one sample, so you can't take away much from it, but you can see that it's doing something sensible. In the paper I referenced there, we run through some of the standard data sets and show that this seems to work pretty well. Here's another example following this person out running. It's a bit painful to watch this video because it's shaking a fair bit, which adds to making the problem a bit more challenging as well. So those were just a few snapshots of evaluating at the high level. At this point, I'm not evaluating, but just illustrating. But in this paper, we do actually evaluate and compare against other methods and show that this comes out very well. And we also give a few other examples. And then we don't necessarily have to work with image data. Here is an example with laser data and three-dimensional object tracking and detection. This is, I guess, from autonomous vehicles, where the task is to spit out these boxes in 3D. And that's of course relevant for all sorts of tasks. And I think that this shows, or I hope it shows, that this combination, which is again what a main message I have here, that this combination of probabilistic models and deep neural networks is quite exciting and promising. I can show you a video of this as well. Where is it? Here we go. So here you see the driver's seat view, and this is the sensor view, and the algorithm output is then these boxes. And this involves not just our regression method, so it's the regression method that solves the problem, but a lot of the point cloud processing and so on, we just borrow existing technology for that. But the regression solution we have is important to get the performance here. So as we keep moving around, we get decent estimates of the positions of the vehicles that are standing by or that are actually moving around. I'll pause there. And what we have been looking into, as we discussed a little bit before, is this proposal distribution, which has to be designed manually, as I explained it, which is a bit annoying. And this is something that we've been able to change and automate this learning of suitable proposals, which has given us better results with less demand of hand tuning. And this is on archive if you want to dive into it. I'm not going to dive into the details there. I'll just and then I'll just briefly want to say that we do spend time on teaching as well, as Carl said. So I'll advertise a new book that we are publishing. It will actually be next year, in March next year, together with Cambridge University Press, which is a first course in machine learning. So this is something that we wrote because we actually missed it, which was interesting given the large amount of books that are available on the topic. But still, for people like me and my fellow co-authors here, so trained as engineers coming into this area, we sort of missed that way of getting into the subject, if I put it like that. So we tried our best and built a course and wrote this book for it. And it's the book is freely available for forever at this website if you want to have a look. So to conclude, what I've been trying to do here is to basically state that solving regression problems with deep learning is not really a solved problem. There are ways of doing it, but we are not finished thinking about how to do it. And what I've tried to do here is to give you one way of doing it, which at least for these tasks that I've shown you give the best results so far. And the idea was to, which I do think is quite intuitive, is that not restrict the model up front, but instead relax the assumptions on the final answer, and let the data do a little bit more of the decision there. And we solved the problem using importance sampling, which we can definitely criticize since it works for low dimensional problems, but in higher dimensions, that's going to be a problem. Then this NCE method, noise contrastive estimation, that we borrowed is probably more interesting. And we get decent results on challenging real world, at least to us, challenging real world problems in this setting. So with that, I think I'll stop and see if there are any more questions.
Thank you very much for a very interesting talk. Any follow-up questions for Thomas? He will also stick around afterwards. Some informal discussions. I think Ankush.
Yeah, thanks, Carl. Thanks, Thomas. That was a very interesting talk. I have a couple of questions. Number one is, could you give me a little intuition as to the size of the networks that you used in perhaps the tracking problem and the amount and type of data that you're providing for training?
Mm-hmm. So we haven't done much, or you could probably do more in terms of actually thinking about what should this network look like. So we have used what people normally use in these different tasks. So we haven't put much effort into that, I should say. Which I guess is both good and bad, because it shows that we can get better results without thinking about that. But I think I'm also confident that if you put someone skilled at that task, we can get even slightly better performance out of it. So these networks are not overly big. It's not something you need a massive computer to run.
So a ballpark of it would be like 10, 20 layers. That would be the size of these things.
Oh yeah. So it's not, and importantly, the number of parameters is not massive.
Okay.
So
okay.
even less layers actually.
And in terms of the data, like, do you need a huge amount of images that are
so we use a fair amount of images and videos, I should say, I guess, for these applications, but nothing more than what's available in the standard data sets out there. So
Sure.
We haven't collected anything new, but we do need a fair bit of training data to get started.
Okay, I see. And the other thing was, in terms of learning the importance sampling, can you give me some intuition, like or the importance distribution, like just a quick sort of intuition as to how you're doing that from data directly?
So I should also say, by the way, if you want to look into this, coming back to your earlier first question, so we have the code is available online, and also much more details about every specific example in the both in the code and to some extent in the paper. So if you really want to see the details, you can have a look.
Thank you.
So in the in training the proposal distribution, we borrowed something called mixture density networks, which is basically what's the short intuition there is. So we used Gaussian mixtures to get started without having to do much. But the problem is, as someone said, of course, that, well, it's a Gaussian and it's just a mean and a covariance. So instead, we're using a representation that's, again, dictated by a network and then weighting a few of them together. So a mixture in the same sense. So then we have a lot of freedom in the proposal distribution as well.
Okay.
So that's the approach that we took.
Okay, thanks. I understand. And my last question was, have you looked into neural processes and the neural process family at all? Those are
with great interest, but only in terms of trying to understand it so far. I haven't really used it. I find it super interesting, that line of work, and it's something that's been coming back in my mind every now and then, but I have never really set time to do something with them.
All right. Thank you. Thanks.
Thank you.
Tim, I think you raised your hand.
Yeah, thanks. I really enjoyed your talk. I had a couple questions. I guess you answered the first one, because the idea of choosing a proposal distribution, you're kind of stuck back in the original problem of how to choose a probabilistic distribution. So I guess you're doing a Gaussian mixture, you were saying, this mixture density for that, and I guess you have to choose a number of modes at that point, a number of elements in the mixture. So that
so you still have to make some decisions, absolutely. But the key point is that we can use some of the data to get a better proposal, so that when we solve our actual problem, then we get better samples and hence better approximations of the integral.
Yeah, well, that makes sense. And then the other question was about why this works. You could look at why this works better for these problems than a straight up direct approach of estimating y from x. And typically for something like particle filtering, it's because this models the distribution better. Like particularly maybe it's not unimodal. So for the two skateboarders, I'm assuming it's because one of them, you had distribution where one mode is on one skateboarder and one mode is on the other skateboarder. And that's why it was able to sort of keep relative probabilities until that became clearer. If you follow me, that the question is, have you looked at what it is about, what these distributions look like and why they do a better job than the unimodal?
Yeah, good question. It's precisely that. And the way we have seen that is by making up academic examples like this one-dimensional toy example I showed you in the beginning, where we know that we have two modes, for example, and then make sure that we that the algorithm spits that out. And then we have also looked at some of the examples real world examples in more detail and see what the distributions look like. And also there we can see that it's precisely what you say, that the method is capable of maintaining several different hypotheses about what's actually going on. And then when more measurements become available, it can zoom in on the one mode that actually matters. But during critical conditions, like when they pass each other or what have you, then it maintains several, the uncertainty increase and or it maintains several possibilities, which of course is automatic for this way of representing things. And I think it's the same reason why the particle filter does well in many applications, is because you don't have to go in and hand code. If this happens, then we should have another mode, and if that happens, we should remove one, and so on. It's handled by this non-parametric representation.
Thank you.
Thanks.
Any more questions? I think it's past noon here in Boston, so I think I will not have the audience hanging around if you don't have any more questions. So thank you again, Thomas, for a very nice talk.